Okay, this is an example of how to draw free body diagrams, and actually we're going to do several here. And these problems are straight out of chapter 4, and you've already listed the forces that go with these situations, and now we're just going to draw how the free body diagram would work. And I've got a grid here just for scale because forces are vectors, so the length of the force vector is supposed to represent how large the force is. And we're going to figure out how large these forces should be based on what's going on in the problem. So for number 1, a flower pot falls freely from a windowsill. Okay, and it's saying ignore air resistance. So that really is free fall. That's our previous chapter. So we already know that it's accelerating, right? So we know that we even know the number. It would be negative 9.8 meters per second squared. Okay, so that means that the net force is not 0. Okay, so it's greater than, well, it would be down, right? But this flower pot is accelerating, so it must have a net force that's causing that. Well, the only force on it, if it's freely falling, is gravity. So this one's easy to draw. It's just only one force. So then it doesn't really matter how long I draw the force vector because I don't have another one like to compare to it. So I would just draw a vector pointing down to show that the force of gravity, to show that the force of gravity is downward. There we go. Okay, for number 2, this is a skydiver, but the skydiver has been falling for a while apparently because now they're falling down but at a constant velocity. So, and that's because of air resistance, right? So we would know that acceleration is 0. We're at equilibrium, which means that the net force must be 0 as well in order for it to be moving like that. So then we need to draw the free body diagram so that all the forces cancel with each other. Well, there are only 2 here. So we have force of gravity. Let's say I'm going to draw that as down 3 boxes on my graph paper here. And then also the force of air resistance, which I would draw pointing up because that's the only way to get the gravity force to cancel, right? So we would show the normal, sorry, not the normal force, the force of friction, we could call it. I'm going to put FF for right now. If you don't have graph paper for these kinds of problems, it's okay with me if you just draw like a congruent symbol from geometry. Okay, that's number 2. Let's do one more. Let's do number 3. And actually I have one on the next page too, so let's bring some graph. Oops. Okay, so number 3, a cable pulls a crate at a constant speed across a horizontal surface. So again, this piece of information is very important. So for number 3, the acceleration is 0 if it's moving at a constant speed. So then again, oops, the net force is 0 as well. Must be. Okay. So then it does say though, the surface provides a force that resists the crate's motion. So that must be friction. Let me zoom in a little. Okay. Then let's draw these forces. So we always draw gravity, right? This time I'll just make it go down 2. That's fine. Okay. this object is not accelerating up or down either. So if we have this crate, okay, it must be traveling across, yeah, it's traveling across a horizontal surface. So that means that there's a normal force from that surface, right? So if this is, you can imagine it sliding across the floor or something. Okay, so the floor is horizontal, but it exerts a normal force because normal means perpendicular. So it's exerting a force up on the crate. And then it's moving at a constant velocity across that surface. It doesn't really say to the right or to the left, so let's pretend it's going to the right. Then it's being pulled by a cable. We use the force of tension for cables. And then it has a force of friction on it. And since the net force is 0, all the forces have to cancel, and I'll have to draw this force of friction the same length as tension. It's also okay, like I just arbitrarily picked this to be 2 boxes, but that wouldn't have to be the same as gravity, for instance. Okay, let's do one more on the next page. Okay, so let's imagine that a soccer ball is rolling to the right on the grass in front of you, and it's slowing down. So if I get my grid here, well, it's rolling to the right, okay? But it doesn't say anywhere that any soccer player is touching it, okay? It's also really important to notice that it's slowing down. So it is moving to the right, but its acceleration is to the left. So one way to think of it is like, what if the right is a positive direction, okay? Then if it's slowing down, its acceleration is negative, which in this case would be a vector to the left, okay? And then the net force is not equal to 0 because it is accelerating. It's just like decelerating is how normal people would say that. So when we're thinking of the soccer ball, we can definitely draw, let's say, a small weight here. It's not accelerating up or down. It's just accelerating to the left. So the normal force is basically the ground holding it up, okay? And that would cancel with gravity. But then the only other force on it must be friction, basically. So if I draw, let's say I draw friction like this one, okay? That vector must be pointing to the left. Remember, friction always points opposite the way the thing is moving. And then I'm not even going to draw an arrow to the right. Yes, it's rolling to the right. That's its velocity. But the free body diagram shows why it's accelerating a certain way.